Okay, first the bellwork problem kind of illuminates the change of base property as well as the product quotient and power property, which are going to be the main subject of different skills related to logarithmic equations. So first off, what's also important as we look at these is for you to conceptually be able to make a reasonable estimate as to what that logarithm value would be. So log 8, that means 10 to what power gives us 8? Well, keep in mind that we have 10 to the 0 equals 1, and then 10 to the first equals 10. So if we have 8 here, that's somewhere between 1 and 10, which means x, which is what the logarithm equals, is somewhere between 0 and 1, probably closer to 10. So we're probably looking at about 0.9. And if you plug in your calculator, 0.9, if we should have been an estimate sign, gives you about what log 8 is. And then log 2 will be a little closer to 1, and then if we find that, that would be 0.3. So one, that's just a good way of a good practice in estimating logarithms based on our knowledge of exponents and so on. And two, that's going to help us illuminate what's called the change of base rule. Okay, so we've seen log base 2 of 8 equals 3, right? 2 to the third equals 8. So now my question is, how can you equate log 8, and I'll write underneath it log 2, with log 8 and log 2, and how could we equate that with the original right here of log base 2 of 8, right? So we know that log base 2 of 8 equals 3. Well, this equals 0.9, and this equals 0.3. What operation could you do with these in order to get 3? Well, we could just try the basics of add, subtract, multiply, and divide. So if we added these, it would give us 1.2 about, which is not really 3. If we subtract them, 0.6, not close. If we multiply them, that gives us 0.27, something like that. Tony said 2.27, so that's not it. But if we divide them, that gives us approximately 3. So if I divide these, I get approximately 3, and if you plug in your calculator, you literally plug in log 8 divided by log 2, it will give you 3. So what that shows us is that log 8 over log 2 is equal to log base 2 of 8, and that's going to help us with the change of base rule. In fact, I'm going to come down and write that in. So this change of base is a nice way of being able to help calculate logarithms. If we have a calculator that we can put that sub value in, it's not really an issue. But if we don't, we can then calculate logarithms this way, where typically B and B are selected as 10 or E, so then we have log x over log A or natural log x over natural log A, but these could be different values as we'll also see within our worksheet. Write an equation relating natural log 6, natural log 2, and natural log 3. Again, natural log 6 is saying e to what power gives us 6. So probably e to the second, I think, is like 7.8, somewhere in there. So 6 would be a little less, and what we find is it equals approximately 1.79. And again, you can look at that on a calculator. Natural log 2 is approximately 0.69. And then natural log 3 is approximately Okay, so if we want our base to be 5, we're going to write log of 5, that's our base. Our argument's going to be 25 to the third, that all is in the argument. And then our exponent is 2 times 3. So why did I do that? Well, we know that 2 times 3 is what this all equals over here. So we got to somehow uncover a 2 and a 3 out of all of this. Now note, all of this is in the argument. This 3 is not the cube of the entire logarithm. It is the cube of 25. So you look at that and you go, well, log base 5 of 25, if I didn't have that 3 there, log base 5 of 25 equals 2, right? Because 5 to the second power equals 25. So this equals 2. So if I take this and I move it out front, like right in mathematics, we do certain operations. They just have to be an accurate operation or a change in the mechanics or the relationship of the numbers notationally. And if we do that, we get rid of that. Now we have a 3 out front, and then we have a log base 5 of 25, and that log base 5 of 25 equals 2. 2 times 3 equals 3 times 2. So that suggests that if we have an exponent in the argument, it is equivalent to moving that exponent out front. So in general, here, if n is the exponent of the argument term, we can take that and move it out front. And so we have n times log base a of x. This right here is considered condensed form. This right here is considered expanded form. And note, when that exponent is a radical, in this form you are going to write it as a radical, right? Like root, square root, cube root, etc. Over here you're going to write it as a fraction. So the square root is 1/2 as an exponent. In this form right here, you would write a 1/2 out front, but if you wanted to put it in condensed form, you move it into there, you wouldn't write it as 1/2, you would write it as a square root. Okay, so now we're practicing skills. These are going to be skills that are going to be relevant in terms of solving logarithmic and exponential equations. Why do we solve logarithmic and exponential equations? Because that's what's necessary if we want to work things with exponential equations, functions, logarithmic equation functions like the ones topics we've been talking about and just starting to talk about. So if I want to expand this in condensed form and I expand it, we have two terms. They're both by multiplication, or they're by multiplication. So when we expand it out, we are going to do addition, log base a of 10 plus log base a of z. Here we have division, so when we expand it out, we are going to subtract z to the third. And log base 6 of 1, that's actually calculatable. If you can calculate, go ahead and calculate. 6 to what power gives us 1? That would be 0. And here, the 3 is in the exponent. That's in condensed form. We want an expanded form, so we go ahead and bring that down in front of it. And then that would just simplify to be negative 3 log of z. And note, I wrote the L with a cursive because then it doesn't look like, for instance, like a 31. And we're really getting confused with our notation. Okay, next we have natural log. So natural log is our base. We can distribute the square root to both parts. And so the square root of x squared is just going to be x. That's the y is in the denominator, so it's going to be minus natural log of the square root of y cubed. And note, we can make that into 3 over 2 as 3 is in the numerator of the exponent, and then this 2 is in the denominator from the index of the radical. Remember, a radical or root is square root is 1/2 as an exponent, and then we can move that out front. So our final answer would be natural log x of negative, and note we're moving out front in front of this term right here, 3/2 natural log y. Okay, the other way, condensing. So we have two terms. So we're going to want two terms when we condense. And note, we want to condense when they have the same base, which they do. So z is the positive logarithm term, and y is the denominator. So we'll write it just like that. Note all this, even though it's written kind of sub right here, this means within the argument of the logarithm. So it's log base 4 of the argument z over y. Here, you have two terms, so we're going to condense it with natural log The 2 will go to the exponent there when we condense. So that'd be 8 squared, which would be 64. Plus, I'm going to move up the, before I condense all the way, I'm going to move up the 5 into the exponent there as this moves up when we condense. And now we can condense this, it's addition, so both of those are multiplication inside. And so we have 64, 5 times z minus 4 to the 5th. Nope, please don't get confused with the subtraction in here. Don't think you can expand that out. You can only expand out when you're in condensed form into expanded form when you have products or division. Not subtraction in condensed form. That's only in expanded form. Okay, here a little more challenging. We can take this one step at a time. So if I distribute the 2 into both, no, natural log is just like a variable. So if I distribute in the 2, it just goes in front of that variable. So when I do 2 times 3, that'll give us natural log 6. 6 natural log x minus 2 natural log x plus 1 minus 2 natural log x minus 1. Note, I'm just taking this one step at a time. I see I have 3 logarithms. All positive logarithms are going in the numerator. All negative logarithms are going in the denominator. So I have natural log, and I'm going to have a division bar. This 6 is going into the exponent, and since it's a positive logarithm, that goes in the numerator. In the denominator, I have an x plus 1 with that squared because that gets distributed. This also gets distributed, so I also have an x minus 1 squared. And that would be your final answer right there. So a couple of questions may come up. One, could I expand that out? Yes, you could. Don't have to, though. It's kind of nice in this factored form. Second, well, these were both subtraction, so why do they both go in the denominator? And we're multiplying the denominator, so if we're multiplying, shouldn't that somewhat be in the numerator? So let's look at it this way. Coming back up to here, if I have just explore why it's multiplication in the denominator. Let's say I factor out a GCF, I factor out that negative. This is what just those first or just those last 2 terms would look like if I factored out a negative out of them. And I can make those brackets. So let's say I just have this. I factor out a negative, and then I have a negative. Inside I have natural log x plus 1 squared times x minus 1 squared. And now this negative gets distributed in, which then gives a negative, or a negative here, which then puts a negative right there, as this is now a part of that. So if I have a negative exponent, then this gets also, this negative is out in front here, so it gets distributed to the negative 2 and the negative 2 in there, which means negative exponents get flipped, and both of them would get flipped. So hopefully, that wasn't the best explanation. I can go more over in class, but that gives credence to why all positive natural logs go in the numerator, all negative natural logs go in the denominator when you're going from expanded to condensed form. Next, we're going to look at this worksheet. You did some of these problems last year where you're looking at a general logarithm like log base b of 6, and then you're given rules such as log base b of 2 is a, this is b, and then this is c, and you got to use these to get these expression in terms of a and b, and this is just a good practice as far as working with the logistics of logarithms. So if I look at 6, I go, okay, how can 6 be related to 2, 3, and 5? Well, I do know that 6 is 2 times 3, so I turn it into 2 times 3, and now I look up here, and I go log base b of 2 is a, and log base b of 3 is b. A quick look at this, and students may go, oh, that's a times b. But in fact, you got to make sure, I would highly suggest expanding this out all the way before you do your substitutions. Because when we do that, we expand it out. Now we see right here, this equals a, and this one equals b. So the answer isn't a times b, it's a plus b. Let's Let's go ahead and take a look at number 3, 27. Well, how can I relate 27 to those numbers? Well, it is 3 cubed, so I'm going to turn it into 3 cubed. And now I expand out. I move this out in front, so I have 3 log base b of 3. Log base b of 3 equals b, so this answer is 3b. If you got to this point right here, students typically go b to the third. This is not the exponent of the whole logarithm. It's just the exponent of the argument. So you have to move it out front to get log base b of 3 by itself before you substitute in. Lastly, we have number 10 here. Number 10 is interesting because, and this is different from what you had last year, you can't do any substitutions because if you look at this base, we have a base of 3b, not b. So we could use the change of base rule, where you do log of the top divided by log of the bottom, where the top, the argument's going to be the argument of the original logarithm, and the argument of this one is going to be the base of the original logarithm. Now, we can select any number we want here, provided that it is the same on the top and bottom. Typically, we select 10 and 10, or we select e and e, so it's natural log over natural log, or log over log for log base 10. But in this case, we want to select b, because that's the base we're working with. And now we have something we can work with in the numerator and denominator. So in the numerator here, log base, that would be b of 5 times 3. In the denominator, we can expand that out to log base b of 3 plus log base b of b. And then we can go one more step. That would be log base b of 5 plus log base b of 3 divided by log base b of 3, which equals b, if I remember correctly. Yep, that's b. So now we have b in the denominator, uppercase b. Log base b of b equals 1. And then in the numerator, we can simplify that as well. So log base b of 5 equals c. Log base b of 3 equals b. And of course, we could flip those around. So we have b plus c over b plus 1, or c plus b over b plus 1.